A very good morning to all of you. We are going to have a look how cyberspace was generated and on how it functions, its ecology. We have been inhabiting this world of ours for a number of years as different species, and we have been always looking towards the future and asking, what is the future? Well, the future, it's always a door that has been opened, a door that has been opened for the purpose of, as we go through, showing us the future. And the future was 2 million years ago, the different species of the family of Homo. This species invented voice, and with it speech. It discovered that we are finite, that we die, invented grandparents, and started honoring the dead. With that, we had an amplitude of time. We fed on space and on time. We can plan, we know ahead. And we are of the same stuff as the stars. From me to the star, only but a small step, dispersed on the casual explosion of bursts, in between the night that's going to be, a night that had been, the solar glory of thought. Well, that's a free translation of our Nobel Prize, José Saramago. But this means that we are made of same stuff as the stars. That's why Millet painted this beautiful, peaceful landscape, people praying for a better world in peace and harmony with nature. Dali, for the same setting, saw war, strife. And that's our nature. We live in between fraternity and fratricide. And in between those, we have invented the future. One of the men that contributed dramatically to our invention of the future is Prince Piotr Kropotkin. He is known for many things, but really is not taught, not even remembered for other things than anarchism and stuff like that. But on the aftermath of Darwin, he wrote an essential book. He wrote it in English. All these other books were written in Russian. But this book is about mutual aid. And of course, in this book he says, okay, Darwin is right. It has been experimentally proved that there is an evolution a la Darwin. The fittest, the strongest, takes the field and takes the day. But then he says, there is a much more advanced way of evolution. Because any species has much more success if its individual members are able to cooperate. And he called his book, he gave the title to his book, Mutual Aid, A Factor of Evolution. And what he says is not the invention of some higher world. No, it's like, it's not love, not even sympathy, that makes a pack of wolves to get together. And we all know that if lions would cooperate, they couldn't be hunted in a pack, as elephants cannot be hunted in pack. They hunt the isolated and sick elephant. And this instinct that slowly developed amongst animals and man in the course of a slow and large evolution that taught both animals and man the strengths that the practice of help and mutual aid bring and the joy that comes with it. Cooperation. Cooperation as an engine for evolution is not yet taught, but it has been essential for us to look for each other, to gather around. That's why we invented the terrestrial roads, the maritime roads, the aerial roads, the roads that are taking us to space. And one in time, that's telecommunication. But this ability to cooperate, it's really the most advanced means of evolution. Darwin's evolution does exist. In the end, my brother, because we were born in the same year, 1947, the transistor followed exactly the same path as we did. There was an evolution a la Darwin. The most adapted wins the day, but the most cooperative is able to increase complexity, and as long as he keeps data simple, he is able to do what has been known as Moore's law, that has dictated a web around the world. Transistors that are mixed together with neurons. We are, in some cases, even able to get neural nets or bred on silicon base. So we have come up with something that's a new being. It's partly born, partly fabricated. And that's where we are. And that's where cyber needs to be. It's where this being, in part born and part fabricated, inhabits. It has, as we have means to represent reality. Models are physical stuff. Representing reality, that we have done and invented, but with only very limited means. It's gesture, maybe it was contemporary with speech, then drawing, that brought to us the written language, and now mathematics. And that's only the mathematical representation of the world. It's only 400 years old. With this representation, the union of born and manufactured is changing the world. Because in 30 years from now, we will be 9,000 million born, the son of women. But manufactured, it will be 1.510 to the 18th. That's in the European and International Convention. It's something like 1 million billion. If they are together, they will be very powerful, a la Kropotkin. And the past has been that every time that we know about something, for instance, how to manage humans, we passed it on and gave those manufactured prerogatives that only humans had. I mean, entering a room, that was entering a building, that was a prerogative only for other humans. But nowadays, those manufactured, they have that prerogative. We have given them that prerogative. And every time we learn with them something, we pass it on also to them. So we are able to manage huge quantities of clients, electrons, people, that work for us and with us, distribution points, all that. But all this is new, and is so new that actually we are building a new society, but is not being driven by social concerns. It hasn't been voted for, there was no debate about it, but here we are. We live in it. It has been growing, sort of lurking there. It's not socially constructed, but it's there. And we have only, again, the four means to represent reality: gesture, speech, drawing, and mathematics. With that, we have built a sort of bed where the non-humans proliferate and where the line of horizon is drawn for the new societies. It's a weird line of horizon because we don't know how this new being is. This new being is able, as we were, to carry on doing cooperation. And we have to cooperate because that's the engine of complexity. We can even have a little game a little simulation where each individual member interacts with another one. We are going to represent that through a line. As the number of interactions increases, the size of the largest groupment of elements will increase. Take element number 8 here. Element number 8, now it's linked to 3, to 12, to 1, to 20, and the size of its group, it's then 4. But as the number of interactions increases, we can actually draw a graph where I have the number of interactions to the number of elements against the size of the largest groupment. And you have here a jump. We call it in physics state change. Well, a state change means that the state here cannot be explained by the properties of the state in here, cannot be explained by the properties of the state here. And that's true. The properties of liquid water can't explain the properties of ice. This change either brings something, a new structure that's organic and functional, or chaotic. If it's organic and functional, you have free energy, you can take out of it something. If it's chaotic, you spend all the energy and in the system, you can't do anything with it. What is the difference between a complex system being organic and functional and being chaotic? Well, it has to do with how data provides you with information content and whether you have a solution for it. In 1881, Anderson has come up with a proof, mathematical proof, in a paper called The Singleness of the Superlative, meaning that every time we can come to define a solution, to search for a solution as the maximum of minimum of a quantity, then that problem has a solution. And that was very good for us. That has come up with in areas that were completely unexpected. And in 1949, this search for the singleness of the superlative, brought about this gentleman Zipf and his book on human behavior and the principle of least effort. Because you see, the least effort, it's a superlative problem, the least. Not even the minimum, it's the least effort. And he called it an introduction to human ecology, because that would be how humans would behave. And he found that out by looking at texts. And what he did was he plotted the frequency with which one word appears in a text, say and here and is the word that appears the most of times. So he ranked it number 1, and then D, number 2, I, number 3, and so on and so forth. And when he plotted the frequency against the rank, he saw that it was an exponential, meaning that 10% of the words in a text contribute with 90% of the text. If I was to plot this in log scales, that would be the Zipf distribution. So the way we represent reality by writing, that's drawing, by speech, is really in the realm of the least effort. So it's a superlative problem. And funny enough, this distribution appeared before with Boltzmann in the level of energy of atoms of any gas. So if you count for each level in this room the atoms with a certain level of energy, you will find that 10% of the atoms account for 90% of the energy in the air in this room. Zipf came up with the text, and in between them, Pareto came with the distribution of property. He meant agricultural property. And there was a sort of singleness here, a superlative. And a superlative can also be found, because we have to solve that thing. When we cooperate, how do we know at the end whether the system, the complex system, is organic and functional or chaotic? And that has to do with information content. When you have data, data provides you with information content. That was Fisher. We have no idea what information is. We have so much idea of what information is as we have of what time is or space. We know what it is till we are asked. But if you are asked, we don't know. But Fisher, in 1925, he came up with the idea that you could actually measure the amount of information a piece of data would give you if the chance of it happen would be P. If you work the maths out, you come up with an evolution of the data given by a piece of information, the amount of information given by a piece of data. It goes from being 0 if the chance of happening is very small, but then it rises very fast. It goes to a maximum, that's superlative, at 1 over E, and then it decreases again as that piece of data becomes trivial. This maximum means that if a piece of data gives you, one single piece of data gives you the maximum amount of information immediately, then you are in a case where you have a complex system, meaning that you have many elements cooperating, but you have an enormous simplicity of data. When this happens, we call it, instead of a new state for for meta, we call it emergent behavior, meaning that the emergent behavior cannot be explained by a previous behavior of the system. It's when you go from being alive to being dead, as being a supermarket, being a chaotic bunch of product, being an army, being a bunch of men. And we can even define and characterize architecture with this amount of information. So if you have simplicity of data, meaning very few data for a large amount of information, then you have a system that's organic and functional. If you need an awful lot, big set of data to get the same amount of information, you are with chaos. Take our example. I think I'm in good health. Well, it's official. I've been to the doctor recently. How much data do I need? Nothing, just, are you all right? I'm all right. Very little data. If I get sick, it's x-rays. Now it's analysis. And the pile of data to know about my health increases so much that I go from the state of being organic and functional, meaning alive, to being diseased. And when I'm diseased, the amount of data is so large that you won't be able to see me anymore. And this can change from the outside, and that's cyberspace. You are in cyberspace, that bed I talked to you about. You have to have simplicity of data inside, but the world outside is all changing. But you have your objectives, and you have an internal capacity for change. So heuristically, I'm going to write a metric. The metric is the information outside, it's the engine for change, like time. This is what happens inside, the amount of information inside. These are the objectives, and that's the internal capacity for change. And I'm going to copy not Pythagoras, because there is no evolution, but Einstein. Here it is the evolution. Time. If you change time, then the coordinates in space must change. So I can do the same in the information domain. That's time, the things outside. C means how we take that in. This is my objectives, whether they remain the same or we can change. That's the internal capacity for change, and that's the amount of information I have inside you. If the world changes, so in the outside this is larger than zero. If the objectives and they remain the same and the adaptation is nil, then you are in big trouble because your entropy will start to grow. But if you change objectives, well, some would say you are not the same. But you can, even if you don't have internal adaptation, you can get your inside to be stable. Or you can remain with your objectives, that's the best. You have an internal capacity for adaptation and remain with the same amount of data to explain how you are. Or you can even do better than that, is change objectives, have a huge internal capacity for change, and lower the superlative, the least effort, the minimum quantity of data to explain most of you. Of course, the C is how you relate to the outside. Manufactured usually don't lie. The ones that are born, either we take out some bits, well, we are not very accurate or even reliable. So we gave C larger than 1. But this equation brings about the possibility of having in cyberspace persuasive technology. Not changing you, but changing the opinion. And this is cyberspace. To persuade. And by persuasion, you can change an awful lot of everything in cyberspace. Because we do, most of our life is done guessing. We would like to forecast and even to foresee, to be certain, not infallible, but certain. And the key to all this has been given by Bernoulli, Jacob Bernoulli, in his book, The Art of Conjecturing, Ars Conjectandi in Latin. On his book, he deals with chance and probability. In those days, they were not taken as synonymous. Chance was something that was a property of the object. It is not part of anyone's knowledge. The coin will flip 50% of the times heads, 50% of the time tails, but it doesn't really help you to predict what's going to be the result of the next toss. So it's a property of the coin. When you come to forecast or even foresee, chance, it's interesting to know, but it's not any good. Probability, on the other hand, in those days, nowadays, even for most forecasting, it's a prediction. It's how certain you are of something it's going to happen. And how certain are you that something is going to happen? Well, you combine arguments. Like a doctor when he examines you, like the meteorologist when he's going to forecast the weather. When he tells it's going to rain or it's going to snow in Guarda, he has satellite imagery, he looks out of the window, and, by the way, when he looks out of the window, what he sees takes precedence over all the other arguments. So, what we do in the art of conjecturing is combining arguments, giving each argument a weight. We call in mathematics the set of pairs, argument, plus its weight, belief system. We can build belief system functions, give them weights, and statistically masses. And with that, we are able to resolve the superlative in the equation. How is it that I'm going to do all this organic and functional? Because in the end, like Zip found out, then we would have a means to write an ecology for cyberspace. And we need one. And to do that, we have to know that we want to be able to go through this image, model, and if you can't have both, or at least you have a mathematical representation of the world. And you know, in nature, you don't have yellow atoms. You don't have, the qualities of things are driven by the interactions in the system. And you have reality and you have its model, or its simulation, or its representation. It should be representation. What you want is to know what are the interactions, to perceive them. Because as I said, there are no green atoms. It's interactions that make them green or whatever. So you have a universe of interactions. When you apply perception to the interaction, you actually create the system. You see what you see. On that system, you apply then the belief system. And when you apply the belief system, you have the observables of the system. But of course, first, you have to know your belief system. And how do you build it? Well, knowledge, through knowledge, deduction, induction, intuition, even if you want, revelation. Once you have the set, meaning the belief system, you have the set called belief system, you can produce the masses, and you can know what in your representation are your observables, what you see. We have in Portuguese a saying that if you don't know, you can't see. And that's true. If you don't know it's there, the belief system will not show it to you. In the end, you have reality and you have the application of perception to the interactions, the system in reality. You have the masses, the universal belief system, all the observables. And if you want, you condense that in this equation. You have the same for the model. Now what you want is to have an adherence between the observables in reality with the observables in the simulation. And you can define a distance between the two. You want this distance, that's Pythagorean distance. You can define this distance and you want it to be equal to 0. And of course you know that you will be doing this iteratively. So you hope that in the limit this is going to be equal to 0. You don't want a situation where between model and reality it's larger than 0. But this confrontation of what you see and what is there, because all is there, but you only see some of it. It has been shown to us in this fantastic painting by Salvador Dali. This is obviously a still life, but this is a still life where all the objects are not still. Actually, he called this painting still life, fast moving. Actually, the only object that could not be still, it's the only one that looks still. It's the swallow. All the rest is moving so fast, which means that Aristotle was wrong and Zeno was right. A thing can, two things, many things can happen at the same time in the same location. The thing is, you will be able only to observe some. And that's why you do what it's called profiling, or if you want, belief system of the different countries in the world, of the different perspectives in the world. And when you do that, you know what you will find each of those cultures will see as observables. They are all there. The one seen by a culture, the other one seen by another, they're all there. But each one only sees what he is able to see. And we come again to this superlative solution by Zipf, the principle of least effort, as the basis of human ecology, and this famous, well, Mandelbrot worked on this, the same as the Mandelbrot set. You worked on this, and there is a better version of this, of rank times frequency is constant. But that's for language. That's data for different texts. This is experimental data for text. This is for, it's fantastic. It's the difference in intervals. And even for painting, when you look into painting, say the Impressionists, and you come up with the power law distribution, even for the suprematists, the Kandinsky's, Malevich, all those, and even for music, number of composers by chamber music according to data, Mozart, Bassum, Concerto, well, all kinds of scores in music, and what was to be expected in the internet. The connectivity of the internet backbone, there you are. Number of connected, that's it. AOL visitors, rank, power law, that's internet. Distribution average number of requests by file size, power law. Document size, number of requests, power law. In the end, access to document track, power law. Which means that cyberspace actually is a least effort, as a least effort solution, meaning that our world, the world where Boltzmann, Pareto, and Zipf found that the atomic levels of energy in this atmosphere in the room, words in a text, properties, land, properties in time, money, properties in cyberspace, 10% explain 90%. They are not always the same in the 10%. So most wars, as most revolutions, is just to change the 10%. That's funny enough. It's always 10%. And from time to time, someone comes up and says, I'll speak for the remainder 90% and gets hold of the 10%. The same distribution. This means there is an ecology for cyberspace. And with the representations we have so far, and that's gesture, speech, drawing, and mathematics, we come up with this solution, which is you have to cooperate to defend and to defend the ecology of cyberspace. You have to have an enormous simplicity of data because that means least effort. And of course, this is because we just have those representations. Those new beings that inhabited cyberspace, those born, and now a union between born and manufactured, in this area of the world where I was born and raised, we had a game for gambuzinos. It was a prank. We spent hours all night. Yeah, the gambuzinos didn't exist. Nowadays, you go out, and the game has been destroyed because of this distribution. Nowadays, you can get Pokemon. And once you get Pokemon, you can almost get anything. And that is why with the least effort, cooperation, and simplicity of data, you can actually solve this problem in between fraternity and fratricide. And this is cyberspace regulated. That's air traffic, an animation through 24 hours. All this happens in cyberspace. Airplanes are driven on cyber. They are regulated. But regulation and principles are different things. And I would rather have principles than regulations. But this shows the world as it is now. Our connectivity in time, in the roads of time, that's cyber, is the same as the one that flies our aerial roads. And may I remind you that we are still a long way from getting law for the aerial roads. People in them, that's when you go on board a 747 or A380. The humans that sit in the cockpit, they are part of the machine and the machine is part of them. And they have been doing an evolution a la Kropotkin, cooperating. And once they cooperate, they would make air travel safe. Although there is hardly law in the aerial roads. In outer space, there is no law. In the web, to be safe on the web, you have to follow its ecology. And that is, cooperate to get much more complex, have an enormous simplicity of data, and please do it ecologically, meaning with the least effort. If you do that, then we will be able to securely and safely be on cyberspace. May I remind you that secure comes from Latin secure, meaning living without a care, and safe means to be protected. But we have to be protected from whom? Well, from us in cyberspace, where we are partly born and partly manufactured. And we are safe if we behave cooperatively, with simplicity of data, and with least effort. And I hope this will inspire you one day of coming up with a true cyber ecology theory. Thank you so much.